Today I am going to take the topic of electric dipole. Basically, electric dipole is consisting of two charges that are equal in magnitude, but their nature is opposite, and they are separated by a very small distance. Let us consider minus q and plus q. These are the two charges. They are separated by distance 2L. This 2L is a very short distance, and we consider in all the derivations its midpoint. So out of symmetry, from the midpoint the distance will be L for minus q charge and L for distance between the midpoint and the plus q charge. So because of that, for the easiness of derivations, we consider twice of the length. So here this opposite charges separated by small distance constitutes the electric dipole. Now we are going to talk about the next very important term, that is electric dipole moment. It is a vector quantity, and it is a product of either of this charge and the distance between them. So electric dipole moment, product of one of the charge, either minus q or plus q. We are just going to take the magnitude of that and the distance between them. So it is q into 2L. You can look here, the SI unit of charge is coulomb and distance is meter. So SI unit of electric dipole moment is coulomb meter. One more thing is there, that this is what we have calculated as magnitude, but electric dipole moment is a vector quantity, and its direction is lying along the line joining the two charges, and it is from the negative charge towards the positive charge. This direction is also known as the direction of dipole axis. Now we are going to take the examples of electric dipoles that are existing in nature. Molecules like Axial and H2O, these are electric dipoles. So what is the criteria? How we are going to mention that this is an electric dipole and this molecule is not an electric dipole? So to understand that, we have to make sure one thing, that each atom is having a positively charged nucleus and it is having the negatively charged electrons. So the molecules in which this positively charged nucleus is and this negatively charged electrons, they are separated. For example, we are talking about the molecules that are dipoles. Here one end of nuclei is positively charged and the other end of equally negatively charged electrons, they are having a gap between them, and that is why they are constituting the electric dipole. Though the net charge on these molecules is zero, but they are separated by the small distance, so that is why they are constituting the electric dipole. On the other hand, the molecules that are not dipole, in them the center of the positive charge and the center of the negative charge, they are not separated, they are coinciding, they are overlapping, they are one over the another. Here the center of the positive charge, that is nucleus, and the center of the negatively charged electrons, they coincides with each other, and this is the reason there is no net electric dipole moment. Electric dipole moment is the product of the charges and the distance between them. Here the distance is not there, that is zero, that is why they are not having any electric dipole moment, and that is not an electric dipole. Examples of dipole are HCl, H2O, and the examples of molecules that are not dipole are CO2 or CH4. So they are coinciding, the negative and the positive center of charges, they are coinciding, hence these are not the dipoles. The lines of forces for electric dipole can be seen here. This is the positive charge and the negative charge. These are the point charges. They are equal in magnitude and separated by a very small distance. You can see these lines of forces for an electric dipole. They are originating at positive pole and they are terminating at the negative pole of the dipole. Now we are going to find out the electric field intensity. It is on a point lying on the axis of dipole. So minus q and plus q charges, they're constituting dipole, and the line joining on it, we are taking any point, say P on this line, where we are having a unit positive charge, and how much that charge is going to experience the electric field due to this dipole. This is what we are going to find out now. Here, the distance between the two charges is 2L, and from the midpoint, minus q charges at distance L, and similarly plus q charges at distance L. The next thing is this point P is at a distance r from the center of the dipole. Every distance is to be measured from the center. Now, the electric field, we are taking even the magnitude due to plus q charge, and due to minus q charge we are taking electric field intensity E2. Now, if you look at the diagram, we need distance also for the electric field. So the minus q charge is at a distance r plus L to the point P, and the distance between this plus q charge, that is the at situated at the point B, the distance is the from the center, this is total r and this is L, so this is r minus L. So we are having the distance plus q, it is r minus L, and the distance minus q, it is r plus L. The electric field E1, that is due to plus q charge, is given by the relation 1 by 4 pi epsilon naught q r minus L whole square. And similarly, we have found out for the minus q charge. Now, at point P, we are having the two electric fields of equal charges but opposite in direction. So, the net electric field experienced by the unit charge at point P will be the difference of these two intensities. So we'll find out E1 minus E2, and solving this, we are getting Q into 4 LR, 4 pi epsilon naught R square minus L square to the power whole square. Now rearranging, we have taken, instead of 4L, we have taken 2L into 2. This Q into 2L is our dipole moment denoted by P. So we have replaced it by P. So we are having the relation 2PR 4 pi epsilon naught R square minus L square to the power whole square. This is the electric field that is experienced by the unit positive charge at point P due to this dipole. Now we have found out the electric field intensity at point P due to this dipole is given by 1 by 4 pi epsilon naught 2 P. P is the electric dipole moment, R divided by R square minus L square to the power whole square. Now, the direction of this resultant electric field is along the dipole axis. Already we have mentioned that dipole axis is from the negative charge towards the positive charge. So this is the direction. Now there is one more condition. If this R is too large in comparison to this 2L, then L square in this expression can be neglected in comparison to R square, and our resultant electric field will come out E equal to 1 by 4 pi epsilon naught 2 P by R cube. Newton per coulomb will be the unit. You can note down one thing here. This electric field is varying to the R to the power 3. If we are taking a point charge, this electric field varies. E is inversely proportional to R square. And in case of the electric dipole, the variation of electric field will be in terms of 1 by R cube. Now in the second case, we are going to find out the electric field intensity at a point on equatorial line of dipole. So uh, first understand the figure. On understanding the figure, the derivation will be very easy. Here we are having minus q and plus q charges that are constituting the electric dipole, that are separated by distance 2l, and from the center each is at a distance l. O is the midpoint, and on this line, that is a right bisector, this is 90-degree angle, we are having a point P at a distance r from the midpoint of the dipole. Now, if you look at these two triangles, A is the point where minus Q charge is there, and B at point where plus Q charge is situated. Now, if you look at the triangle APO, this is a right angle triangle, and the other one is POB. These two triangles are congruent. Because of that, these two angles will be same theta. Now, the electric field due to plus q charge, that is taken E1. E1 is the electric field due to this plus q charge. So the direction will be from B to P. The electric field due to minus q charge, that is E2. The direction will be, because of the nature of this negative charge, the direction will be from P to A. So if you look at this point P, E1 and E2 can be taken as the two arms of the parallelogram, and in the vector addition we have learned that if there are the two sides of the parallelogram, then the resultant of those two will be given by the uh, diagonal of that parallelogram. So we want to find out the resultant of E1 and E2 at point P, let it be E. And making this a parallelogram, the diagonal is from P towards this point, say S. So P to S is the diagonal that is going to give the resultant, that is what required here. Now, this parallelogram is taken over here in the figure B, and this is resolved in the two directions, perpendicular and the parallel directions. This E1 is separated into its components, it is resolved. Similarly, E2 is also resolved. To find out the electric field at this point P, this is the diagram that we have taken here for the elaboration to find out the resultant value. So you can look at this diagram. The sign components that are perpendicular, they are equal in magnitude, because these are the magnitude of the charges is q, but they are in opposite direction, so they will cancel out each other's effect. On the other hand, these two components, E1 cos theta, that is the parallel component, in E2 cos theta, they are along the same direction and along the diagonal of the parallelogram where electric field is to be found out. So these two will be added up. So we will find the resultant intensity at point P, that is E, given by E1 cos theta plus E2 cos theta. Now, E is equal to E1 cos theta plus E2 cos theta. We'll put the value of cos theta. Look at the diagram. This angle in this triangle is theta. So cos theta is based upon hypotenuse. So L upon under root r square plus L square. So putting the value of cos theta and E1 is q by 4 pi epsilon naught, and the distance is r square plus L square to the power 2. So putting these values, we will get E equal to 2ql 4 pi epsilon naught r square plus L square to the power 3 by 2. Now this q into 2l is our electric dipole moment, so it is replaced by P. So E is equal to P 4 pi epsilon naught r square plus L square to the power 3 by 2. If R is very large in comparison to L, so this R square will be more and L square can be neglected. So we will have E is equal to P 4 pi epsilon naught r to the power 2 into 3 by 2. So 2 cancels and it comes out to be P 4 pi epsilon naught r cube. So the electric field at point P is found out to be equal to P by 4 pi epsilon naught r cube, where P is the dipole moment. Here, if you look at the figure, here the direction is from the positive charge towards the negative charge. So it is anti-parallel to the dipole axis. Our dipole axis is from negative charge to the positive charge, and in case where the electric field is to be found out at the equatorial point due to the electric dipole will be in the opposite direction of dipole axis, or it is called as an anti-parallel to the dipole axis. Here is the comparison of the electric field at a point on the axis of a dipole and electric field at a point on the equatorial line of a dipole. We see that electric field intensity due to a point on the axis of dipole, it is 2 times in comparison to the electric field at a point on the equatorial line of a dipole. One more difference is there. The direction of this electric field is along the dipole axis, that is from negative charge to the positive charge. On the other hand, electric field at a point on the equatorial line of a dipole is in along the anti-parallel axis of dipole axis, that is, it is from the positive charge towards the negative charge. Further, if we compare the electric field due to a single point charge, that is equal to 1 by 4 pi epsilon naught q by r square, and that of a dipole for a point lying on the axial line, the E is given by 2p by 4 pi epsilon naught r cube, and for a point on the equatorial line of the dipole at larger distance, E is given by p by 4 pi epsilon naught r cube. If we compare the results of the electric field due to single charge and due to dipole, we see that the electric field dependence, that is 1 by r square in case of a single point charge, is replaced by 1 by r cube dependence in case of dipole.